Hello, future engineers. Welcome to my YouTube channel. To keep me going and refreshed, please don't forget to share my videos if you like them. And of course, don't forget to subscribe. By conjugate beam method, compute the slopes and deflection at C. Moment of inertia ABC is I, while moment of inertia CF is 1.5 of I, and E is constant. This is the given figure. So first portion ABC is simply supported, so let's consider the first. Summation moment about C equals 0. Then we have By times 5 minus 25 times 7 equals 0. So By is equal to 35 kilonewtons. So if By is 35 kilonewtons, then the shear just to the left of C should be 10 kilonewtons downward. 35 minus 25 minus 10. So this should be 10. And by action reaction, then we have C just to the right, 10 also upward. Then we compute for RE. We sum up moments about D considering CDE. So counterclockwise positive. Moment about D equals 0. So RE times 8. RE times 8 minus 10 times 6. Then minus 32 times 15. The centroid is 7.5 from either F or C. So if this is 7.5 and this is 6, so this is 1.5. So minus 32. The moment is clockwise. So minus 32 times 15 times 1.5 equals 0. So R sub E is equal to 97.5 kilonewtons as shown in the figure. We then replace this loading into concentrated load 32 times 1 and couple, which is 32 times 1 times 0.5 as shown, which is 16 kilonewton meter. 16 kilonewton meter is 32 times 1 meter times 0.5 at E. So let's now prepare the moment diagram by parts and then the equivalent conjugate beam. So we select points B and D as, no, C and D as moment centers. So 25 times 7 is 25 times 2 is 50 over EI. 25 times 7 is 175 over EI. 35 times 5 is also 175 over EI. Then at D, we have 10 times 6 divided by 1.5. 10 times 6 divided by 1.5 is 40 over EI. Then due to this loading here, 32 times 6 times 3 divided by 1.5, second degree. So that's 384 over EI. Then due to 32 kilonewton per meter times 1 times 0.5, 16 over 1.5, 16 over 1.5, that second degree is 32 over 3 EI. And let's have the moment of the 32 kilonewton per meter. 32 times 8 divided by 1.5, so we have triangular loading here. 32 times 8 divided by 1.5 is 512 over 3 EI. Then moment due to this 32 kilonewton per meter load, 32 times 8 times 4 divided by 1.5, second degree. The height is 2048 over 3 EI. Then the moment of the 37.5, 97.5 at D, 97.5 times 8 divided by 1.5 is 520 over EI. So this is the complete moment diagram by parts. Let's now transform the beam into conjugate beam. So this is fixed, interior hinge, internal pin, hinge, interior hinge, fixed, as shown. So fixed, interior hinge, internal pin or pin, interior hinge, then fixed. So that's the transformation from real to conjugate beam. So if we look at the conjugate beam, portion DE is the only simply supported, and we want theta D first, as shown. This is the positive direction of the slope as well as at E. So let's just consider DE. To solve for theta D, we sum up moments about E equals 0. So theta D times 8 plus this area times moment arm 2/3 of 8 is 16/3. So plus 0.5 of 8 times 520 over EI times 16/3, 2/3 of 8. Then minus 8 times 32 over 3 times 4, or equals 8 times 32 over 3 times 4 plus moment of this area 0.5 times 8 times 512 over 3 EI, 2/3 of 8, 16/3 moment arm. Then this area is 1/3, 8, 20, 48 over 3 EI. Since this is 8 over 4, 2, so its distance from E is 6. So minus or plus 1/3 of 8 times 20, 48 over 3 EI times 6. Because this is 8 over 4, remember 8 over degree plus 2, so 8 over 2 plus 2, so 8 over 4, 2. So it's the distance of centroid of this area from the right is 6. So from here we can compute theta D, and theta D is positive 4288 over 9 EI. Having found theta D, let's consider CD. So we have theta C right and delta C. If you look at the figure, delta C is common, but the slope just to the left and just to the right are expected to be different. So these are the positive directions of slope and deflection. So to solve for theta CR, because theta D is known, just summation versus Y. So theta CR plus the area of this triangle, which is 0.5 or 1/2, 0.5 of 6 times 40 over EI. Then minus the area of this spandrel, 1/3 minus 1/3 of 6 times 384 over EI, minus theta D, which is 4288 over 9 EI, equals 0. So we can now solve theta CR. Theta CR equals 1124.444 over EI. Then for delta C, so that theta CR is not involved, we sum up moment about C, right? So clockwise positive, delta C plus the moment of this area, so plus 1/3 of 6 times 384 over EI. This is 6 over 4 or 1.5, so the distance of the centroid from the left is 4.5. 6 minus 6 over 4. 6 over 4 is 1.5, so 6 minus 1.5, 4.5. So delta C plus this moment of area, then plus theta D 4288 over 9 EI times 6, then minus the moment of this area of triangle, minus 0.5 of 6 times 40 over EI. 2/3 of 6 is 4, moment arm equals 0. So from here we can solve delta C. Delta C is negative 5834.667 EI. Finally, let's consider BC. Let's transmit the values. So we have theta B, and here downward as positive theta C left, and delta C counterclockwise, because this is now the right section. So to solve for the theta C left, remember that this is trapezoidal loading between B and C. So if we divide this into triangle, we have identical triangle. One is above the beam, 175 over EI, and one is below. They have the same distance from the left, so therefore we will ignore this triangle and the triangle, identical triangle, which is in this trapezoidal figure. So we will only consider this triangle with length 5 meters and height 50 over EI. So summation moment about B is 0, considering BC. So clockwise positive. So theta C left times 5. Because this is downward for this triangle here, plus 0.5 or 1/2 of 5 times 50 over EI. 1/3 of 5 is 5/3, the moment arm. Then minus delta C minus negative of negative 5 or minus negative 5834.667 over EI equals 0. So we can now solve theta C left. Theta C left is equal to negative 1208.6 over EI. So that's it for this problem.